Hi everyone. Embark on a journey through complex scientific problems with me, your hostess Melanie. We'll unravel physics mysteries step by step, from the quantum realm to classical phenomena. In this inaugural video, we'll dive into the fascinating world of quantum mechanics, specifically exploring the quantum harmonic oscillator in momentum space. We will be solving problem 3.11 from David J. Griffiths and Darrell F. Schroeder's Introduction to Quantum Mechanics, 3rd edition. This problem is a perfect starting point for our channel as it combines several key concepts in quantum mechanics: wave functions, Fourier transforms, and the relationship between classical and quantum physics. We'll walk through the process of transforming from position space to momentum space using the Fourier transform, a powerful mathematical tool that links these two representations. Along the way, we'll discuss the nature of the quantum harmonic oscillator and its importance in physics, and how it differs from its classical counterpart. We'll explore the concept of the classical forbidden zone and why quantum mechanics allows for phenomena that would be impossible in classical physics. Whether you're a student grappling with quantum mechanics or simply curious about the bizarre world of the very small, this video will provide valuable insights and problem-solving techniques. Now, let's embark on our quantum adventure and unlock the secrets of the harmonic oscillator. The problem asks to find the momentum space wave function, phi, as a function of momentum and time, for a particle in the ground state of the harmonic oscillator. What is the probability, to 2 significant digits, that a measurement of p on a particle in this state would yield a value outside the classical range for the same energy? Hint: look in the math table under normal distribution or error function for the numerical part, or use Mathematica. A linear harmonic oscillator exhibits simple harmonic motion, SHM, which is periodic motion where an object oscillates back and forth along a straight path. This model applies to diatomic molecules like hydrogen at small displacements or low energy. At larger displacements, the motion deviates from harmonic behavior and is anharmonic. To simplify analysis, SHM is often modeled using an ideal spring attached to a mass on a frictionless surface, eliminating dissipative forces that would decrease mechanical energy in a system. This idealized model provides a foundational understanding of oscillatory motion. In equilibrium, the spring has no potential energy stored due to no deformation, and has no kinetic energy due to no movement. When displaced, the system possesses both forms of energy. As the spring stretches or compresses, its potential energy increases. A restoring force acts to return the system to equilibrium. The restoring force is directly proportional to the displacement and acts in the direction opposite to that of displacement in accordance with Hooke's law. F equals minus kx, where k is the spring constant, or more generally, the force constant, and x is the displacement from the equilibrium position. The negative sign indicates the force opposes displacement. During the oscillation, due to inertia, the object's resistance to changes in motion, the system overshoots the equilibrium position. This causes the restoring force to work in the opposite direction, perpetuating oscillation or simple harmonic motion. In classical mechanics, work is defined as the product of force and displacement under 2 conditions. The force must be constant and parallel to the displacement. This straightforward equation applies to scenarios like pushing an object on a uniform horizontal surface against friction. Initially, there is acceleration as the object is brought from rest to a constant velocity. Once the object is moving at a constant velocity, the applied force exactly equals the frictional force. The frictional force equals mu mg and remains constant. M is the mass of the object, g is the acceleration due to gravity, and mu is the coefficient of friction between the surfaces. The coefficient of friction is determined experimentally and depends on the materials involved. The force remains constant if there is no acceleration or changes in the surface properties. In contrast, for a harmonic oscillator, the restoring force is variable, changing with displacement as the system oscillates. As we previously discussed, the force is given by Hooke's law, F equals minus kx. When graphed on a force versus displacement plot, this relationship produces a straight line with a negative slope passing through the origin. To calculate the work done by this variable force over a displacement, b, we consider the area under the curve from x equals 0 to b. Because of the variability, small changes in displacement, dx, correspond to different values of the force, as illustrated in the graph. The work done can be approximated by summing the products F times dx for each interval. As these intervals become infinitesimally small, we approach the exact value of total work done. This process is formalized in calculus as integration. Therefore, the work done by the restoring force of a harmonic oscillator from the equilibrium position to some displacement b is given by W equals the definite integral from 0 to b for f dx. The work-energy theorem states that the net work done on a system equals the change in its kinetic energy. This applies to all forces but is particularly useful when dealing with conservative forces, such as the restoring force in a harmonic oscillator or gravity. A defining property of conservative forces is that the work they perform depends only on the initial and final positions of an object, rather than on the path taken, allowing the work to be expressed entirely in terms of potential energy. For instance, the work done by gravity depends only on the change in height, while the work done by a spring depends solely on the change in its displacement from equilibrium. In both cases, these differences directly correspond to changes in potential energy. Therefore, when dealing with conservative forces, the work-energy theorem can be expressed in terms of total mechanical energy, defined as the sum of kinetic and potential energy. Furthermore, in a closed system influenced only by conservative forces, the total mechanical energy remains constant. This conservation means that any increase in kinetic energy resulting from positive work is accompanied by an equal decrease in potential energy. Consequently, the work done by a conservative force equals the negative change in potential energy. The negative sign indicates that as kinetic energy increases, the stored potential energy decreases correspondingly. To calculate the change in potential energy between two positions, we use the potential energy function U of x. The change in U of x is given by U of x final less U of x initial. Since only changes in potential energy matter, we often assume that the initial position has zero potential energy, simplifying the equation to just U of x final. In this way, U of x represents the potential energy at the final position. For a harmonic oscillator, we can derive the equation for potential energy by integrating the negative of the force. We can then use Hooke's law to express the restoring force. Finally, we can perform the integration. The result is the potential U of x equals 1/2 kx squared, where, as we have previously seen, k is the force constant and x is the displacement. Angular frequency, or omega, is commonly used in the study of harmonic oscillators and waves rather than the force constant k. This scalar quantity represents the rate of rotation or oscillation and is measured in radians per second. 1 radian is the angle subtended at the center of a circle by an arc equal in length to the circle's radius. Radians reflect how far along the edge of the circle we travel relative to its radius. Simple harmonic motion, SHM, is closely related to circular motion. SHM can be visualized by imagining a point moving at a constant speed around a circle and projected onto a straight line. For a harmonic oscillator, angular frequency is used in the equation for potential energy. It relates to the force constant k and mass m by the equation omega squared equals k over m. This relationship is derived by starting with Newton's law, F equals ma, and substituting acceleration as the second derivative of position with respect to time, and then setting it equal to Hooke's law, or minus kx, where x is displacement as was previously discussed. A specific case with the motion starting at rest from maximum displacement or a fully stretched position is captured by a particular form of its general solution, given by x of t equals a cosine of omega t, where a is the amplitude and omega is angular frequency. X of t is differentiated twice to find the acceleration in terms of omega. Since x of t equals a cosine of omega t, x can be substituted into the second derivative. By comparing the two second-order derivatives, we can see that k equals omega squared m. Consequently, this version of the force constant can be used to express the potential energy of a harmonic oscillator as u of x equals 1/2 m omega squared x squared as shown. The energy dynamics of a harmonic oscillator can be effectively visualized as potential and kinetic energy diagrams. These curves manifest as complementary parabolas, which are a consequence of their quadratic relationship with displacement x and the equations having opposite signs of x squared. The kinetic energy curve appears as a downward-facing parabola that is explained by the equation derived from the conservation of energy relationship. Ke of x equals E minus 1/2 m omega squared x squared. The potential energy has an upward-facing parabola with equation U of x equals 1/2 m omega squared x squared. The maximum displacements or amplitude are shown on the graph at x equal plus or minus a. This parabolic relationship with displacement creates the restoring force that pulls the oscillator back to its center and driving the characteristic back-and-forth motion of a harmonic system. An ideal spring maintains the same total energy for a given amplitude, ensuring the system's state always lies on the parabolic curve in accordance with energy conservation principles. This can be visualized by treating the potential curve as a well with a ball representing a particle exhibiting SHM. The graph also shows forbidden zones outside the potential curve where the oscillator cannot exist, representing energy levels beyond the system's capacity and where energy conservation would be broken. Although a quantum harmonic oscillator is a quantum system, in order to better understand the quantum system's behavior, the classical potential energy curve is used. At high energies, the quantum system approximates classical patterns, a concept known as the correspondence principle. Thus, the classical curve helps bridge our understanding between the quantum and macro world. The green curves depict wave functions psi of x, representing quantum states associated with different energy levels. Psi of x is a complex valued function that describes the quantum state of a particle in each quantum system. Wave functions can be used to determine the probability distribution of where the particle is likely to be found or have a specific momentum. In a stationary state of a quantum system, measurable properties like average position, average momentum, average angular momentum, when applicable, and energy remain constant over time. When a particle is in a state where these properties and the probability distribution remain constant, it is in a stationary state. Unlike classical mechanics, where energy is continuous, quantum mechanics restricts the energy to discrete levels. This means that energy can only take on specific, discrete values that are denoted by the quantum number n, where n equals 0, 1, 2, and so on. Each curve corresponds to an energy level and a specific wave function. As the quantum number or energy level increases, the wave function exhibits more nodes, indicating greater complexity in its oscillatory patterns. A node is a point where the wave function passes through zero as it shifts from positive to negative or negative to positive. As a result, there is zero probability of finding the particle at a node. The squared modulus of the wave function is interpreted as the probability density, which refers to the likelihood of finding the particle within a small range around a specific location. The squared modulus is multiplication of the wave function with its complex conjugate, which is denoted by psi asterisk of x. To find the complex conjugate, change the sign of the imaginary part. This ensures we always get a real, non-negative probability density, regardless of whether psi is real or complex. Integrating this density over the entire space equals 1, ensuring proper normalization and that the particle exists somewhere in space. The probability density remains constant over time for a stationary state. The quantum harmonic oscillator is described by the Schrödinger equation, which is equation 2.5 in Griffith's book. Here, h bar is the reduced Planck's constant, m is the mass of the particle, psi is the wave function, v is the potential energy, and E is the total energy of the system. We can adapt this equation specifically to the harmonic oscillator by substituting into the equation the angular frequency, which was previously discussed. Equation 2.45 in Griffith's book. Unlike classical particles, the lowest energy state or the ground state has non-zero energy and is known as the zero-point energy in quantum mechanics. If a quantum particle were to be at rest at the bottom of the potential well, as classical physics would allow, we would precisely know both its position, i.e., x equals 0, and momentum, i.e., p equals 0. This is forbidden by the Heisenberg uncertainty principle, which states the position and momentum cannot be known simultaneously. The ground state probability density extends beyond the classical turning points of the potential well denoted by plus or minus a. It has a Gaussian shape, i.e. a normal or bell curve, centered at x equals 0, and reflects the highest probability of finding the particle at the center of the potential well and spreading outside the well in both directions. The highlighted regions outside the potential curve are classically forbidden areas where a particle with this energy could never be found according to classical physics. In quantum mechanics, there's a non-zero probability of finding the particle in these regions. This phenomenon is known as quantum tunneling. It demonstrates that quantum particles can penetrate barriers that would be insurmountable in classical physics. Griffith's problem 3.11 asks, what is the probability of finding the particles in these classically forbidden areas? To establish the quantum boundary conditions for the harmonic oscillator, we first consider the classical boundary conditions. As pointed out during the discussion of the work-energy theorem for conservative forces, the total mechanical energy is conserved. E equals k plus u, where k is the kinetic energy and u the potential energy. The kinetic energy of a particle with mass m and velocity v is given by k equals 1/2 mv squared. The momentum p is related to mass and velocity by p equals mv. Therefore, velocity can be expressed in terms of momentum as p over m. Substituting this into the expression for kinetic energy gives p squared over 2m. As seen previously, the potential energy for a particle displaced by x from the equilibrium position with a force constant k is given by u of x equals 1/2 kx squared, where x is the displacement from the equilibrium position and k is the force constant. Thus, as shown here, the total energy of the system can be shown in a more convenient form. Next, the problem requires the momentum space be considered. Shown here is the result of rearranging the total energy equation to solve for momentum. As was previously discussed, for a harmonic oscillator, as the mass passes the equilibrium position, the mass reaches its maximum velocity due to the restoring force. This results in maximum momentum. Since the displacement from the equilibrium position is 0, the potential energy is also 0 at this point. This allows us to eliminate the potential energy term, leaving only the kinetic energy. This defines the classical range of momentum for the harmonic oscillator as momentum equals plus or minus the square root of 2 times the mass times energy. This indicates two possible momenta, one corresponding to motion in the positive direction and the other to motion in the negative direction. This double-valued boundary for momenta reflects the harmonic oscillator's oscillatory motion. The particle passes through x equals 0 twice per cycle, once moving in the positive direction and once in the negative direction. Problem 3.11 specifies using the same energy level for the ground state of a quantum particle in the harmonic oscillator potential. The energy levels, found by solving the Schrödinger equation for the harmonic oscillator, are given by the quantum number, plus 1/2 multiplied by h bar times angular frequency, equation 2.84 in Griffiths. Setting n equal to 0, the energy for the ground state of the quantum harmonic oscillator is h bar times angular frequency divided by 2, equation 2.61 in Griffiths. Therefore, the quantum-based range becomes the absolute value of momentum, p, less the square root of mass times h bar times angular frequency. To solve problem 3.11, the position space wave function, psi of position x and time t, for a particle in the ground state of a harmonic oscillator potential is the starting point. This wave function is then subjected to a Fourier transform to obtain the momentum space wave function. Griffiths equation 2.86, shown here, represents the normalized harmonic oscillator stationary states, where h sub n of Kazai are Hermite polynomials, mathematical functions expressed as a sum of the powers of Kazai, where Kazai equals the square root of m times omega divided by h bar times x. Kazai is a dimensionless variable used to simplify the expression, introduced by Griffith in equation 2.72. This transformation streamlines our calculations and helps us focus on the essential physics. As previously mentioned, normalization of a wave function occurs when the integral of its probability density modulus over all space equals 1. The first two terms in the equation serve as normalization constants to ensure this requirement is met. The first term ensures the wave function is appropriately scaled based on the physical parameters of the system, mass and angular momentum. A smaller scaling factor would stretch the wave out, making the particle more likely to be found further from the center. Increasing mass or angular frequency further leads to a smaller length scale, resulting in a more tightly confined wave function where the particle is more likely to be found near the center of the potential well. The second term is a factor that adjusts for the quantum state n. It reduces the overall amplitude or height of the wave function for higher n states, making the wave function more spread out and oscillatory, but with a smaller maximum amplitude. As n increases, this factor decreases, ensuring the wave function remains normalized and orthogonal at each energy level. Interestingly, these wave functions can be expressed as a product of a Hermite polynomial and an exponential term. This polynomial determines the shape and nodal structure of the wave function for each energy level n. As previously mentioned, the number of nodes in the wave function increases with n, corresponding to higher energy levels. The exponential term gives the wave function its overall Gaussian shape and ensures it decays to 0 at large distances. When the wave function decays, it means that as the position x becomes very large in the positive or negative direction towards positive or negative infinity, respectively, the wave function gets closer to 0. This decay ensures that the wave function can be normalized, satisfying the probabilistic interpretation of quantum mechanics. Hermite polynomials are orthogonal in the context of the quantum harmonic oscillator. In mathematics, orthogonal means that two functions are independent in a specific way, which is quantified by an inner product. For Hermite polynomials, this inner product involves integrating the product of two Hermite polynomials weighted by a Gaussian exponential function. The inner product determines the degree of overlap between two different functions. The exponential weight function emphasizes values near x equals 0, giving less importance to higher values of the absolute value of x. Explicitly, the orthogonality condition can be written as shown for n not equal to m. Their orthogonality ensures that different quantum states, energy levels, are mathematically distinct and do not overlap, which corresponds to physical states being independent of each other. The specific Hermite polynomial used in the equation depends on the energy level n. The Hermite polynomials are listed in the Griffith book in Table 2.1, with some values displayed here. As noted earlier, the ground state of the quantum harmonic oscillator corresponds to the stationary state where n equals 0. According to the table, the Hermite polynomial when n equals 0 is h sub 0 equals 1. Since 2 to the power of 0 and 0 factorial both equal 1, by definition, the second term also reduces to 1. These two simplifications significantly reduce the complexity of the equation for the ground state wave function. To fully characterize a quantum system's behavior and as required by Problem 3.11, a time component must be appended to the equation. This time component, or wiggle factor, the term mentioned in footnote 3 in Chapter 2 of Griffiths, introduces a sinusoidal or wave-like oscillation through a complex exponential. By applying the method of separation of variables, the Schrödinger equation can be split into spatial and time-dependent components. For a stationary state, the time-dependent component is given by phi of t equals e to the minus iet over h bar, equation 2.6 from Griffiths. As previously shown in the discussion of the momentum boundaries for the quantum harmonic oscillator, the energy for the ground state is derived from Griffiths' equation 2.84 and equals 1/2 h bar multiplied by the angular frequency. The complete position space time-dependent wave function for the harmonic oscillator in its ground state, phi sub 0 of position x and time t, is then obtained by combining this time-dependent factor with the previously derived spatial component. Fourier analysis is a powerful mathematical tool that decomposes a complex function into its simpler building blocks and is used in physics, signal processing, engineering, economics, and other fields. The general Fourier transform is given by Plancherel's theorem, a fundamental principle of Fourier analysis, as shown in Griffiths' equation 2.103. In the context of position and momentum, f of x represents the position space wave function psi of x, while f of k is its Fourier transformed counterpart, corresponding to the momentum space wave function. F of k has a negative exponent and integration over x, and is conventionally defined as the Fourier transform of f of x having a positive exponent and integration over k. F of x is defined as the inverse Fourier transform of f of k. The Fourier transform breaks a function into its constituent frequencies, or in this context, momenta. The inverse Fourier transform reconstructs the original function from its spatial frequency components. The wave number k describes the spatial frequency, representing how many wavelengths fit into a unit distance. It is measured in radians per meter, defined as 2 pi over lambda. Plancherel's theorem, a fundamental principle of Fourier analysis, guarantees that the total probability of a particle's existence in all of space remains invariant, regardless of whether it's calculated using its position or momentum wave function, underscoring the inherent equivalence of these two descriptions. The momentum wave function is denoted by phi of p. Mathematically, Plancherel's theorem states that the integral of the modulus squared of the wave function, integrated over all positions x, equals the integral of the modulus squared of the momentum wave function, integrated over all momenta p, is equal to 1. While Fourier transforms are often expressed in terms of the wave number k, in quantum mechanics it is more useful to work directly with momentum p due to the fundamental relationship between momentum and wavelength as described by de Broy's hypothesis. De Broy's equation relates a particle's wavelength lambda to its momentum p using Planck's constant. K is defined as 2 pi over lambda as previously shown. Substituting lambda in terms of p, the wave number is obtained as shown. Then both sides are multiplied by h. Solving for p yields a clear relationship between momentum and wave number k. Since h over 2 pi is the reduced Planck's constant h bar, a substitution results in momentum equal to h bar times k. The wave number equals momentum over the reduced Planck's constant, which can be substituted into the exponential terms, changing ikx to ipx over h bar for both the forward and inverse Fourier transforms. This effectively replaces the wave number with momentum in the exponents, and consequently, the function f of k becomes f of p, reflecting the transformation from the wave number domain to the momentum domain. Next, the derivative of both sides is taken, yielding dk equals dp over h bar. This is then substituted for the dk in the inverse Fourier transform. Now, since the equation is scaled by 1 over h bar, this constant can be factored out of the integral and included in the normalization constant. However, remember that equation 2.103 used 1 over the square root of 2 pi as the normalization constant. This arises because there are two forms of the Fourier transform, the asymmetric and the symmetric forms, as mentioned in footnote 41 in Griffiths. In the asymmetric form, the normalization factor is applied only to the inverse transform, keeping the forward transform in a simpler form. On the other hand, for the symmetric form, the normalization factor is split into its square roots, allowing for an even distribution between both the forward and inverse transforms. Consequently, the same applies to the h-bar scaled normalization constant, resulting in a normalization constant of 1 over the square root of 2 pi h-bar. This symmetrical form can make mathematical manipulations, derivations, and proofs cleaner and more uniform, especially in theoretical contexts like quantum mechanics. Since the objective is to find the momentum space wave function, the position wave function and momentum space wave function are plugged into this version of the Fourier transform, giving us the final form of the Fourier transform, as shown in equations 3.54 and 3.55 in Griffiths. The equation for psi of x and t in the ground state of the harmonic oscillator derived earlier is substituted into our equation for the momentum space wave function Fourier transform. Any terms that do not involve the integration variable, x, can be treated as a constant and moved outside of the integral sign. Next, the exponentials inside the integral are combined by summing the exponents. The exponent in the form of the general quadratic equation, ax squared plus bx plus c, needs to be transformed by completing the square, resulting in a binomial squared, x plus a squared. In this case, a modified vertex form of a binomial squared is desired, minus a times x plus b squared plus k. In this form, A equals m omega over 2 h bar, B equals minus ip over h bar, and k equals 0. Just as a side note, the vertex form of a quadratic equation has special significance. The point bk represents the vertex of a parabola, which marks either its maximum or minimum value depending on whether a is positive or negative. The modified vertex form is derived from the standard vertex form of a quadratic function a times x minus h squared plus k, where the vertex is at hk. Instead of using h, b is introduced such that h equals minus b, and substitute minus b for h, which simplifies to ax plus b squared plus k. In many physics and mathematical contexts, particularly in Gaussian integrals, the quadratic term often appears with a negative sign to ensure exponential decay when used in an exponent. This leads to the final modified form where the negative sign applies to the entire squared term. To achieve the goal, the second term, ipx over h bar, is multiplied by 2m omega over 2m omega, which doesn't change the value of the equation. This clever manipulation creates a common factor of minus m omega over 2h bar. This common term can then be factored out. Now the quadratic expression can be rewritten by adding and subtracting the square of 1/2 the linear term. Why half of the coefficient of x? This choice comes from the need for a binomial squared in the form x plus a squared as previously discussed. Expanding the binomial squared yields a perfect square trinomial. Notice that the a in the squared binomial is 1/2 of the trinomial's middle term coefficient. By adding and subtracting the square of the middle term's coefficient, the expression remains unchanged while allowing for completion of the square. The first 3 terms in the expression, a trinomial, can now be converted to a binomial squared, x plus ip over m omega squared. The common factor can then be distributed to the 2 terms. Since I squared equals the square root of -1 multiplied with itself, I squared equals -1. Therefore, I squared p squared equals -p squared and can be substituted into the expression. The right term is then evaluated, resulting in the final form of the exponent. This final form is substituted into the exponential in the equation for momentum space wave function. The exponent in the integrand contains 2 terms. The second term is independent of x and can be factored out of the integral. The remaining exponential has the aforementioned vertex form, with b equal to ip over m omega and a equals m omega over 2h bar. The integral is now in the form of a Gaussian integral. The variable a must be a positive real number, otherwise the integral diverges and has no solution. The standard or canonical form of the Gaussian integral found in most integral tables and math textbooks is shown. We can let u equal x plus ip over m omega, and therefore du equals dx. U and du are substituted in the exponent. A is replaced with m omega over 2h bar, giving the result shown. The final term in the expression can be rewritten as the square root of 2 pi h bar over m omega, since dividing by a fraction is the same as multiplying by its reciprocal. The Gaussian integral is now identical to the integral portion of the momentum wave function equation. This allows the substitution of the integral with the solution for the Gaussian integral. It is possible to simplify the constants into a single constant. First, the constant terms are grouped on the left side. The first 2 terms are combined into a single square root. 2 pi h bar appears in both the denominator and numerator of the square root and can be cancelled. To make calculations easier and more straightforward, radicals such as square roots, cubic roots, etc., can be expressed as powers with fractional exponents. This allows the use of exponent rules for simplifying radicals. Furthermore, fractions under a radical can be rewritten using negative fractional exponents. Consequently, the first term, a fraction under a radical, can be rewritten as m omega to the power of -1/2. The second term can be rewritten by separating the numerator and denominator into distinct terms, with the numerator raised to the power of 1/4 and the denominator raised to the power of -1/4. The 2 m omega terms can then be combined, resulting in m omega to the -1/4 power. Finally, combining the last 2 constant terms gives m omega pi h bar to the -1/4 power, or 1 over m omega pi h bar to the 1/4 power. The result is the final form of our momentum space wave function for the ground state quantum harmonic oscillator as a function of momentum and time. According to Born's generalized statistical interpretation of quantum mechanics, as discussed in section 3.4 of Griffiths, the probability of measuring momentum, p, between an interval a to b, is given by the integral with respect to momentum from a to b of the squared modulus of phi of momentum p and time t. The squared modulus of phi of pt represents the probability density function of momentum and equals phi of pt multiplied by its complex conjugate. By definition, for any complex number z, the modulus z squared equals z multiplied by its complex conjugate. The complex conjugate, as defined earlier in the lecture, is obtained by replacing I with negative I in phi of pt. The classical boundary for momentum in the quantum harmonic oscillator using the ground state energy level, as established earlier, is bounded by the absolute value of p less than or equal to the square root of mh bar omega, where m is the mass of the particle, h bar is the reduced Planck's constant, and omega is the oscillator's angular frequency. For the ground state, there is a non-zero probability of finding the momentum of the particle in the previously defined classically forbidden regions. The probability greater than the square root of mh bar omega represents the combined probability of finding the particle in the classically forbidden momentum regions, specifically outside the range from the negative square root of m omega h bar to the square root of m omega h bar. As reviewed earlier in the lecture, the potential u of x in the quantum harmonic oscillator forms a symmetric parabolic shape. This symmetry results in a probability distribution for momentum that is also symmetrical around the line p equals 0. Leveraging this symmetry, the total probability within a specified range can be calculated by integrating over the region of positive momentum and then doubling the result. The momentum space wave function and its complex conjugate can be substituted into the probability equation. The complex conjugate term has the sign of I reversed, as per the definition. The two time-dependent exponentials cancel out and are eliminated. This means that the probability distribution of possible momentum values remains fixed for the ground state, a stationary state. The probability is constant in time. The two normalization constants are combined using exponent rules. The final two exponentials are also combined, resulting in the final equation. The equation can be simplified by using substitution with the goal to remove the physical units, mass m, angular frequency omega, and Planck's constant h bar, from the equation. Let u equal p over the square root of m omega h bar. Differentiating this gives du equals dp over the square root of m omega h bar. The integral can now be written in terms of variable u. Rearranging the equation for du, dp equals the square root of m omega h bar times du and is substituted into the integral. The variable u is dimensionless, which means it does not carry physical units. Instead, it rescales the momentum such that momentum is measured in natural units of the harmonic oscillator at the ground state energy level. It was derived previously to be equal to the square root of m omega h bar. By setting p equal to the square root of m omega h bar in the equation for u, the result is one natural unit. 1 is therefore used as the integral's lower limit. The integral is further simplified by eliminating the square root of m omega h bar, resulting in an equation expressed in terms of the dimensionless variable, u, which, as required, represents a number without physical units. This final form of the equation facilitates evaluation using standard mathematical techniques, particularly for calculating probabilities. It represents the area under a special type of curve known for its bell-like shape, commonly referred to as a Gaussian curve, which was introduced earlier. A key property of this curve is that the total area under it, when properly scaled or normalized, equals 1. This ensures that it represents a probability distribution. As shown previously in the discussion of harmonic oscillator energy levels, the ground state is a Gaussian distribution. However, solving this integral directly is challenging. To handle such problems, mathematicians use a function called the error function, written as ERF of x. This function calculates areas under the Gaussian curve between 0 and any given value for x. The area under a specific portion of the curve represents the probability of a random variable falling within that range. Taking advantage of the symmetry of the curve, it is multiplied by 2, yielding the area from x to negative x. To calculate the probability of a particle's momentum measurement being in the classically forbidden zones, as discussed earlier in the lecture, we need the area of the two tails on either side of the curve, which represent x to infinity and minus x to minus infinity. A related function, the complementary error function, or ERFC of x, is used. It is defined as 1 minus ERF of x. It's like taking the total area under the curve, which is equal to 1, and subtracting the area between the points, x and negative x, leaving the area of the tails as a result. To find the value of ERFC of x, calculators, math tables, or programming languages like Mathematica, available online, are used. An example is shown. Entering the value 1, which corresponds to a natural unit as discussed, or 1 standard deviation in statistical terms, yields 0.1573 as the probability. Therefore, the probability that a measurement of momentum, p, on a particle in the ground state of the quantum harmonic oscillator would yield a value outside the classical range is 15.73%. Rounding to two significant figures results in 16%. This reflects the inherent uncertainty in quantum description of the particle. Furthermore, the ground state is where the particle is at lowest energy state and exhibits minimal motion, yet there is still approximately a 16% probability that the momentum measured is outside the classical range. This highlights the profound differences between classical particle and quantum particle descriptions of physical systems.